Yeah.
Okay. So last week we talked about understanding feature selection techniques in machine learning. And if you could remember very well, we did talk about what feature selection means, why it is important. Remember, we talked about the issue of multicollinearity. We also talk about dimensionality reduction issues. We talk about computational issues that also arises. And then we also talk about improving the accuracy of the model. And finally, we talk about issues that has to do with overfitting. And then we also talk about interpreting the model. Feature selection actually makes it very easy for us to focus on the features that are much more important. So we also talk about the types of feature selection method, where if you remember, we talked about the filter method, the wrapper method, the embedded methods, the hybrid, and also the assemble feature selection techniques. Then we also went further to talk about the advantages and disadvantages of each of those methods. And then we also further talk about a brief about the hybrid method and then the assemble method, and then finally we talk about the best practices. So today we're going to follow up from there to look at the practical section of the class. How do we implement these future selection techniques that we looked out for? So what I'm going to do, uh, I wanted to look at a classification problem and a regression problem. Of course, I always want to start from the regression to the classification. So it seems to be quite much what I've done under the regression problem, because remember we are looking at each of these future selection techniques. So for today, after this class, I'll share the script for the regression. Then within the week, I will share the script for the classification. And if possible, maybe we could talk about it a bit in the next class before we moved into post-hoc model interpretation. Remember, we talked about the interpretation techniques that we're going to be looking at. That's the sharp, the line, and other explainable AI approaches. That's the next area we want to go. So, but like I was telling John yesterday, I'm a bit at this junction divided in a sense that I want to introduce you guys to approaches that could speed up your coding skills, while on the other hand I'm also torn about maintaining tradition in order for you guys to know the theoretical frameworks that guide these approaches. So I've been thinking about it because the reason is there is a breakaway from the normal traditional coding pattern since the emergence of the generative AI. So I'm a bit thinking of, should I use the generative AI to help you guys in speeding up, or probably we should understand it first and then we go into it. So those are the two conflicts that is in my mind. But on the other hand, I wouldn't want to deprive you guys of using the Gen AI because it's really going to help you guys to master these skills. However, the major setback is that if you don't know these things, you don't just understand the outputs you are getting. So I'm really, really thinking about the best way I could create a link to make you guys to be able to use these technologies effectively. However, I'll think about the best approach to go with it. But I'm also open to you guys' suggestions. But really, I want you guys to be able to start using these technologies. For example, over the week I was excuse me, I was thinking I was using it to generate some codes within splits of minutes. These are things that ordinarily if I'm to build them, it would take me some time, and all that, but I could do that within a couple of, so I was a bit divided about it. But notwithstanding, let's see how it goes, and then I'll think about the best approach we could follow it. Anyway, excuse me. So today we're going to start from the regression problem in the feature selection approach. So we will look at each of the methods that we have talked about. We'll look at the filter method, the wrapper, the embedded method, and so on. We'll also look at how we could use models like logistic. Okay, so that will be for the classification problem, not this one. But we'll also look at how you could be able to generate this useful insight. So, but like I always say, most of the time I'm confined to use the health problem data set because most times I apply in the area of health, and I really want to explain these things in such a way you guys could understand it better. But notwithstanding, even if you are in finance, even if you are in agriculture or any sector you find yourself, these methods are the same. So they don't really change. The only thing is understanding how you could integrate the domain knowledge effectively in those areas. So like I always say, you have to study your hypothesis. Make sure you understand your hypothesis. So that will guide the kind of analysis you're going to do. But once you understand the hypothesis, it's always going to be in line with the already laid down frameworks. So future selection in health wouldn't change if you go to finance. It wouldn't change if you go to space science. It's always going to be the same approaches. It's just that the problem is the future selection is more of a domain related. So the kind of approaches you use are not universally the same. So meaning that sometimes you have to find a way to use so many of those features in order for you to come to a consensus, and then you could be able to now select the right features. So, and then another thing again, the input from the domain experts is very relevant. So, like I told you guys in the last class, don't just do these things in isolation, because you can select a feature or remove a feature that may not really be statistically significant, but you end up seeing that that feature is actually important, from the domain context. So it's very good if you're doing feature selection, always work with the domain expert. And then when we talk about domain knowledge, it doesn't have to be with the experts, like the persons themselves, but rather we can also look at it in form of literature. You have to do your literature review so you can be able to understand from literature, for example, what are the risk factors, or what are these factors that have been identified by previous experts. Then knowing that would actually guide you in selecting the futures. So don't just rely on the computational approach alone, but rather work with all these holistic frameworks in order for you to come into a sort of a reliable, robust approach of selecting the features that you need. So today, the data set we are going to be focusing on is a data set on mental health. So if you looked at the title, we say uncovering stress patterns in teenagers using machine learning. Now, this data set is a Kaggle data set. And I don't know if that I actually mentioned about Kaggle to you guys, but if I'm not mistaken, I did. So Kaggle is
You did.
good. So it's a framework where you see lots of data set and competitions where experts put in different data set. For example, you could see this is a data set on nutritional breakdown of food. You can see a data set on online retail and e-commerce data set. There is also another one in air pollution in China, 2015 to 2025. So that's the time series data. And so many other data sets, you could see them. If you remember, one of the data set we talked about last time on the fraud, this was the data set we used. And then we also talk about stock sense, if you remember, this where we picked that data set. So the data set on mental health, this is the data set that we are going to be using in the study. So the data set have a user ID, it have the age of the participant, because of course we are looking at teenagers, so we'll say 12 or 13 years, so around 19 we consider as teenagers. Then we have gender, which is a male or a female. We have social media hours, which is the hours spent on social media per day, hours spent exercising per day. We also have okay, good. We also have sleeping hours. We have screen time hours. We have survey stress score. We have wearables stress score, and then we have a support system, and we have academic performance. So each of this data set, you could see how each of them are being scored. Like the survey stress score is from 1 to 5. Wearable score is within the range of 0 to 1, for example, and all that. So you can look at this problem from two angles. You can consider this problem as a classification problem, where, for example, if you want to predict the survey score of how stressed someone is, you would also use, for example, let's say the wearable stress score. You can use it to see if that person is because it's from 0 to 1. So the closer that score is to 1, it means that person is stressed. So that would be more like a regression problem. So any of the angle you come from, you can actually use the data set for any of them. So depend on what you want to do. So you could actually see, and the reason I'm doing this is because I don't want to pick a data set that is so large because of the computational efficiency. This is just an example. However, in real world data set you could be meeting, they are actually much. And I think I could actually look for let me see if I can okay. Let me see this script as well. I could show you guys example of what I mean in real world data set. This is from my PhD. I think I could share because these are in public repositories, so it shouldn't be an issue. So in this study, for this one, this is one of the analysis I did years back on my PhD work on genetic data set. You can see I have the sample ID. I have each of the columns are genetic variants. Now, if you look at it, you can see we have 975 columns. So it's actually much, compared to what we have, just 11 features. So it could be much. So in the case of like this one, I needed to do some sort of filtering to check for multicollinearity. You see, I only visualized the top 15 to see how they are. Then I did some select k-best approach to make sure I pick those features that are quite important. Then from there, I used sort of a lasso to help to shrink them. And then I think after the lasso, the features reduced. If I'm not mistaken, it reduced around 200 and something before I started doing the machine learning and all that. And even though you could still see that the scores were not much, and I expect that because the genetic variants most of the time may not be that strong, except you include other data set like demographic data set, probably age, gender, and all that before you start seeing the score goes up. But I just wanted to show you that in real world, you can have data set that are quite much. It's not just going to be small, you know. So, but in the case of this example that we are looking at today, we are just looking at 11 variables. So they are not much. You can see they are just very, very small. But imagine if experts want to take up the most important features to use them in, for example, developing the right therapy. They can't work with all these 11 features. It's kind of much for them. So they will want to focus on just a very few features, is what they want to focus on. So in that kind of situation, you have to make sure you find the features that are most important in predicting the stress, mental stress in teenagers. So the first aim of the study is to identify behavioral and psychological indicators associated with elevated stress level in teenagers using a feature selection approach. Then the second part of it is to validate a robust machine learning model capable of predicting, sorry, this is supposed to be teens, not adolescents. Anyways, teens stress level and all that. So we are going to we'll see how we could achieve these two aims. So the first thing, like I said, this will be each of the objectives of what we are going to do, how we're going to see if we could create some features, and then how we can apply each of the feature selection techniques. So let's give it a try. Let's go now and see how we could do that. So the first thing, like I always used to say, you load the required packages. And then if you don't have any of those things installed, remember to use the pep installed and then the name of the package. And then you could be able to install that. So for example, we didn't have this package in our Jupyter notebook. So we just have to make sure we put it in our files before we go on. So the first thing we do, we will run this, which is what we have done now. Okay, first of all, let me just clear everything so we don't have to have some overlapping. Restart kernel, clear out this. Okay, nice. So we could start them afresh. I think it's better. So the first thing is to run load the packages, like I said. So by the time you load them, they take a bit of time. Okay, okay, good. Sorry. Yeah, it has run. Sorry. So the first thing now is to call the dataset. So like I used to say, you can download the dataset directly from Kaggle. So when you go to the Kaggle, you will see there is an API on how you can be able to download the dataset. I think once you click on the download, you will see the API, and then you can copy this API back to your Jupyter notebook and you can be able to call the dataset. So it is the API we use to call the dataset. Now, in order for you to do that, you will need to look out for the name of the dataset, because this one will only give you the zip file, but the dataset is inside the zip file. So in order for you to be able to, you try to see what is the CSV saved. So you could see this is actually the name that the CSV file is saved. So this will call the folder. Then when it calls the folder, remember the folder is zipped. So you need to know where is the CSV inside the folder. So the CSV was saved. So you make sure you use the right name, else you will get an error. So you could try that to see how you could call the dataset from using the API, okay? The first filter method we are looking at is correlation. And I already talked about much on this correlation. So you already now know that what the correlation is focused on is to assess if there are multicollinearities, and then it says, and then how do you know these multicollinearities? Most of the time, they are likely features that have correlation coefficient above 0.8. Most of the time, those are the ones you will be targeting. So it will make sense if you can see these features and then assess it. But in this case now, we are not going to be assessing like we use the heat map. Although the heat map is nice, but I wanted us to try something new. So that's why we used the bar chart. But now you can clearly see from the bar chart that the first thing you can see is that we do not have issues of multicollinearity. All the scores are very small. I think the highest is around 0.033, which is very, very good. And then the correlation coefficient we are looking at here is the absolute value. Because remember, when you looked at the heat map from the previous slide, sorry, you would see that the heat map was actually showing us some correlations that were negative. I don't know why this is not coming up. Okay, it's fine. It was showing us some of those things that were negative. So because of that, it makes sense if you put it in absolute, so you can be able to see them from the bar chart. And of course, correlation is a two-way sort of thing. So that shouldn't be an issue. Okay, let me refresh to see. This is taking time. Anyway, let me see if I could show you guys this. Yeah, so I didn't do something like this. That's what I just wanted to show you guys. Okay, it's come up. I don't think I had lots of features that are delaying this from coming up. Okay, let me open it again. Probably this should be the issue. Okay, let me just try to open features. No. Okay. Great. Okay. So let me close this one. Choose selection. Okay. Great. Okay, but now I think I will have to. No, this was the futures one. Okay. Okay, yeah. So let me just run it again. I don't know why it was hanging. Okay. So I think we're here. Good. So we're in the future selection correlation. So like I said, if you look at the correlation that we had here, it's taking time. Okay. Good. Now, if you look at it, you could actually see we did have some negative. So that was why we tried to take the absolute value. So that could help us to capture a much better pattern. So that's what we did here. Good. So, and again, we highlighted the top 5. We just wanted to see the top 5 futures. So the first thing it means the first thing we could see, even though I'm not comfortable with gender because gender is a categorical variable. So I would not take it serious. We're not supposed to include the gender for the correlation because it's 1 or 0. So we don't need that. So let's just look at the ones that are, so like age, social media hours, exercise hours, stress score, and maybe academic performance. We're not supposed to consider gender. So then so let's say these are the top variables that are coming up when you look at it, and this actually makes sense because I could say the more you age, the more strength you are. So also social media hours and exercise also contribute. And so that's why it's good for you to take exercise serious, okay? It's actually important. So the analysis of variance approach. Remember when we were talking about the filter method, we said there are several filter method approaches we have, like correlation, chi-square, information gain, ANOVA, and all that. So all these ones are Rapper's method. So the ANOVA, of course, ANOVA, we said it's analysis of variance. Is also a way that we could use to select features that are related or associated with the response variable. So first of all, we need to perform something called select k-best, which helps to rank them. Because if you look at the correlation we did, we also try to use the absolutes to sort of perform the ranking. So that's why you see we display them based on their importance. So by the time you do for the ANOVA, and if you know ANOVA very well, remember what we are looking at in ANOVA is the Fisher score. If you come here, you will see that I think there was a place we did talk about the Fisher score. Yes, this one here. So we are interested in the Fisher's score for us to use as our statistical measure. So that's what we call the F test. Yeah. So you when you run the ANOVA, again, we see age as a top feature. We also see social media hours, we see stress score, we see gender, we see support system coming up. Then sleeping hours, academic performance, and so on and so forth. We're not that much. But we can see age, social media, all that. Those are the top features. So let's find features that are common to both of them and see. Good. So when you now this is a Venn diagram. Of course, it's you're all mathematicians, so I definitely expect you guys have a good knowledge of that. So looking at the Venn diagram, you could actually see that we had a very good number of features that are common to the correlation and also to ANOVA. 4 features are common. It's just one features that are common to the both of them. So this is more like intersection, eh? Of course, I'm very sure you guys know that. Okay, so the second method we are looking at is the wrappers method. So the wrappers method, remember we said in the wrappers method, you looked at things like forward selection and backward selection and recursive selection approach to remember wrappers. We said if you have these features, you feed them to the model recursively in such a way that you can be able to eliminate or you can select forward or backward elimination, or you could do it recursively to find it. So remember one of the advantage, if you notice in the filter, you could see it was done rapidly. So that's one of the advantage of the filter method that we said last time, that it's very fast and inexpensive. The features are done without necessarily training the model. It also helps to remove redundant or highly correlated features, which I've already shown you guys from here. Now, the problem of the filter method that we said is that it does not consider interaction between the features. So that makes us to understand that these things don't happen in isolation. So it makes sense if we can be able to look at how these features are interrelating with each other sometimes. Remember that for the players that are playing in the field, they have to pass ball to each other. They cannot just continue to be playing individually. No, they pass until they score. So the filter method is somehow saying each player has to work on their own to achieve that score, but which is not true. We need them to work collectively as a team. So that's one of the limitations because it's more like a one-to-one relationship between the target variable, ignoring the contribution of others. So the wrappers method helps us to deal with that. However, the problem of the wrappers method is that it's computational and expensive because we now have to iterate each time we go. So it's either the recursive sort of selection that it does makes it to be computationally expensive. But so if we imagine a situation where I told you guys we have up to 900 and something features, by the time you are doing the wrappers method, it will be really, really stressful because you have to go over all of them, which is not going to be funny. So the first example we are looking for the wrappers is the recursive feature elimination method. So first, for this case, you will see it won't take time as such because we just have 11 features or 10 features. So they are not much, but even the 10, you can see it did take a bit of time to run them. So you can imagine a situation where we have lots of them. And even in the recursive elimination method, we're still using a random regression, which is even faster. But you can imagine the situation where we have lots of them. And I wish I could show you guys an example of this feature selection. I used to have a very nice looking example of it. Feature selection statistical approach. Let me see if it's this one. I did have one that I did some years back. I like the way it used to appear. I think it was this one. No, not this one. I think. Good. You can actually see how much these features they could be very, very crazy. Let me see if I could. Maybe it should be this one. Embedded. I used to have one that looks so nice. I need to show you guys how it comes out. No, it's not this one. Yeah, this is not this one I wanted to show you guys. Let me see. Hmm. Oh, each connection always. I can't, and I don't want us to lose time. Our time is almost up. Anyway, um, yeah, I think I can't remember seeing the script, but if I happen to come across it, I will show you guys what I mean. Very nice plot that it came out. I so much like the way those plot looks like. So but in that case, I can't remember how many futures I was dealing with in that situation, but it was looking very nice plot. Anyway, but if I come across it, I'll share it with you guys. So the next thing is to rank the futures. Remember, we select them, so we rank them again. So once you run this, the next thing for us to do is to visualize them again. Yeah, so remember this is recursive elimination. So it means to do that. So when you look at it, you see that gender male standout support system is also in academic performance and stress survey score. So these were the features that were not eliminated. It eliminated all these features here: the screening time, sleeping hours, exercise hours, social media hours, but even age. So you could see the Rapper's method is saying age is not important. But remember that the filter method said age. We see the age coming up in all of them. Age was important, but the rappers is saying no, it's not. So you can see they are not this universal method to all these things. But now let's see as we go further what the other approach will say. So let's look at the sequential future selection. So again, remember we did have the filter, the wrapper. Yeah, so we just did the recursive elimination. So let's look at the sequential future selection. So now in the sequential, so it will be taking them one after the other, either in a forward manner or in a backward manner. So, but this one will be looking at it from a forward manner. So again, we run it. Then let's look at the top five. Yeah. So again, in this case, you could see that you could see that it said okay, age, social media, exercise. No, I think those were the top selected now. Right. So age, sleep hour, stress score, support system, academic performance. So those were the features that were uh eliminated or selected. Or how would I say? Okay, let's see the Venn diagram. Good. So in the Venn diagram, you could see two features are common to the both of them, while three features are not common in each of them. So for the forward selection, we have social media hours, screening time hours, exercise hours, sleeping, and age. While in the forward selection, that's the sequential forward selection, we have survey, stress score, academic performance, support system, sleep hours, and age. Now, let's look at another approach again, which is the embedded. So remember, the embedded method comes the other way around. So the embedded method performs selection by combining the model training. So it sort of combine the advantage of the filter and wrappers method. So it also seems to be faster, and also it seems to generalize much better. So the lasso regression is one, the decision tree is one, the gradient boosting is one. So let's see what happens. So I think in this example, we are looking at lasso. Now, so we run it, but again, let me make an emphasis. In the case of the lasso, if you don't scale the future, you will likely have issues. Although I think in our own case, the scaling should not be an issue. I think we have already scaled. Well, I'm kind of leaving it out for you guys to know. Always scale before you do the lassos. If not, one feature will be dominant compared to the other ones. So don't forget that. So let's look. So, but in the case of lasso, one of the things you will struggle with is to find the optimal alpha. It's find the optimal alpha. That's where you always try to struggle. So most of the time, in order for you to overcome that problem, you use some sort of a cross validation, this CV equals 5. So that could help you to be able to find the optimal. But I think in our own case, the optimal was around 0.05. So if you visualize it, you'll see that it's only age that met that threshold. So again, that's one of the issues that I used to have with Lasso, because it do shrink most of the features towards 0. So if you have a lot of features, then you could use the Lasso. But when you don't really have lots of features, I don't really advise, because it will end up pushing all the features to 0 for you. And by the time you do that, you lose information. So always use it when you have lots of features. So, and then again, be careful. So you can see it's only age that it's able to identify as the most important feature. It's screen all the other features. Then remember, the second example we said is the decision tree random forest. So let's see what the decision tree random forest will tell us in the absence. I would prefer you to use random forest or decision tree or embedded, because like I said, you could lose a lot of information in Lasso. So let's visualize what we have. Good. So you could see in the case of the random forest, it said exercise hours, sleeping hours, social media hours, screen time hours, and age are the 5 top most important features. So again, could output them. So I would rather want to go with this, because you could see it actually pick age that Lasso identify and also identify other 4. So the next thing we talked about that day was the hybrid method. And if you remember vividly, we said the hybrid method is usually the combination of these approaches. We say either you combine 2 or more of the filter, wrapper, or embedded method. So one of the combination gives rise to the hybrid. So a good example is the stability selection method or the hybrid method. So what the stability selection method does is that it will combine some sort of approach coming in from Lasso, and then it will use it and some sort of a bootstrap. I think I should try to teach you guys about bootstrap and sampling stuff before I make emphasis on this resampling and bootstrap. Okay, let me see if I could find time to tell you guys about that. So what the stability will use is that it sort of generate this so many random samples. Now I remember when I was reading about this bootstrap in my PhD days. The example was they used was like a boat, a shoe boat that it could help, so it helps to bootstrap the person. Anyway, so the bootstraps will help to generate or synthetically help us to generate these samples, and then we could find out some averages from them. But I'll find time to really talk more about it. So the stability help us to create this resampling from these bootstraps, and then we can use the lasso to again shrink them. So by the time we define that, we do some ranking, and then we will see what happens. So it's again, we are looking for the most stable future. That's just in summary what this stability is looking for. The features that will be stable no matter how you generate the samples in such an infinite finite manner. So again, when you looked at it, you will have a sort of a threshold score. So the threshold score here was 80, and I think none of these features actually meets the threshold. So the bootstrap method, I don't think it's quite effective in this case because it didn't actually detect any of the features that we could keep. So again, yeah, so this is empty. So the next thing we do again for the hybrid method is to do what we call future reshuffling. Now, this future shuffling is very important, especially when you are trying to look out for when you are doing explainable AI. In explainable AI, one of the things we used to do is to try to reshuffle the futures to see which of the future is actually relevant. So sometimes when you reshuffle the futures, you could actually lose some sort of uh, robustness in your model. So that's where we do a lot of future reshuffling is done in that area. So sometimes I used to put it inside the model to do that. So what it does basically is to carry out what we call permutation. So do some permutation and combination to reshuffle the futures for you. So we use the random regressor and then we carry out the permutation feature importance. I did this especially when we are really looking at features that are stable, features that you can actually say this feature is robust no matter what. Then the reshuffling is what you should go for. It's really help you to design because there is this whole idea that the normal future importance you get from regression is not robust. That at some point, when there is some distribution shift in the data set, you are likely going to see these features will not turn out to be important. So that reshuffling helps you to know if these features will be robust when you deploy them. So again, let's see. Social media in this case, it's robust. It's selected exercise hours, sleeping hours, screening time, survey score. So we can actually see that despite the fact that random forest did say that age was important, but when you did the permutation important, you can see that age did not make it. You see, age was displayed, and then survey score came in. So that's one advantage of the permutation feature importance. It's actually tell you that this feature, no matter what changes, they would be much important. So that's why I always like to perform that. So remember, also we talked about embedded feature selection, where we say the embedded combine all of them and vote. So it assemble, no, sorry, not embedded, assemble. It assemble all the characteristic of the other features and then it vote for them at the end of the day to get the final feature set. So what we are doing in the embedded in this case, we are combining all the features selection methods we use in order for us to select the final features and the final features we are looking at is the features that have at least 3 votes in the data. You can increase it to 4. You can even increase it to 5. Say the features that have at least 5 votes in all this method, you should select them as the top features. So you see, we pick feature from we start with correlation, we go to ANOVA, we go to the forward selection, backward selection, Lasso, random forest, the stable features, and also the permutation feature importance. So we pick all of them and combine them. So this as assemble method helps to bring them together. And when we start looking at some machine learning approaches, you see how we can use assemble method called bagging to combine things like random forest, support vector, KNN, and so on. We can combine them to build one super model. So it does that. So again, we are looking out for the consensus feature, and the consensus feature is select based on what the feature has at least 3 votes. So now we would run that. Good. So when you do that, you could see age stand out as the first feature that has more than 3 votes. In fact, age has around 5 votes. Social media has 5 votes. Exercise hour has 4 votes. Stress score has 4 votes. Sleeping hour has 4 votes. And then sleeping time has 3 votes. Then we see gender has just 2 votes, support system has 2, and then academic performance has 1 vote. So in other words, now you can see if you are to go by this ranking and maybe you are focused on only 5 votes, then you will say you automatically these ones will not make it. It's only 2 features that will make it, that will stand out. So it means that the 2 features that will stand out to predict your stress score are age and social media. Then, by the time you make up your mind on the futures, you can now put them in the final modeling pipeline. So now you can now use it to build the final model. But I wouldn't take that today because we have exhausted our time. So, but I'll try to finish up the script with the final model. Then you can be able to use it. So this is how you can do future selection in a very robust way to come to identify the final features that you need effectively. So I think with that, I've come to the end of the class. Sorry, I took 9 minutes of your time. If you have any question, go ahead.
Thank you very much. This is quite interesting.
Thank you.
My eye is getting to open. I also realized that the feature issue is actually a very big research area that in machine learning that one will need to delve into, because
Yes.
there are a lot of work that probably don't take cognizance of this multicollinearity stuff and don't even care on how over the system is overfitting or not. You get a very high accuracy and you think that you have a good model.
Exactly.
Okay.
Anyway, another thing again is that sometimes it's not really an issue in every case, because there are situations where you don't need the future selection issues. You don't need them. So it's not every situation